alternative form of Euler-Lagrange equation. Our main result so far, is the Euler-Lagrange equation that we wrote in the following form. Or in the usual notation, we can write it as partial derivative of f with respect to y minus full derivative with respect to x of partial derivative of f with respect to y prime equals to 0. We solve this for an unknown function y, solve for y of x, and when we do so, we find that the following functional becomes stationary, which we write as delta s equals 0, where s is defined as definite integral on interval from x1 to x2, and function f, a known function, we can call mother function, that tells us how we combine y, its slope y prime, and x into this integral. Now, today we will learn another form of Euler-Lagrange equation which is particularly useful for certain types of f. If f is not an explicit function of independent variable x. So our goal is to rewrite this equation in such a way that the alternative would be useful whenever partial derivative of f with respect to x is 0. Well, we can start out by writing full derivative of f. Here we can use chain rule so since f depends on x, y prime and y, we will write it first for the last argument, then partial derivative of f with respect to y prime, and then full derivative of y prime with respect to x, and finally partial derivative of f with respect to y and full derivative of y with respect to x. Now we can do some simplifications. This is 1. This here we'll call y double prime, and this here we'll call y prime. So we can write this full derivative as df dx equal to partial derivative of f with respect to x plus partial derivative of f with respect to y times y prime, and plus partial derivative of f with respect to y prime, y double prime. Now, so far what we can see in here, that this term, the second term, looks like one of the terms in the Euler-Lagrange equation, with the exception of this y prime. So, in hopes to acquire the second term in that equation, let's write full derivative of another product. We'll write full derivative with respect to x of y prime times partial derivative of f with respect to y prime. So this is a derivative of a product. We know how to handle that. So first we get y prime, and then full derivative d dx of partial derivative of f with respect to y prime, plus now we get the second term multiplier df dy prime, and then full derivative of y prime, which gives us y double prime. So now we can recognize that in fact this term here, the first term, does look like the second term in Euler-Lagrange equation. So let us therefore subtract second equation from the first, and let's see what we get. So we can, on the left hand side, factor out the full derivative with respect to x, and then we have f minus y prime partial derivative of f with respect to y prime, and then we can move the partial derivative of f with respect to x to the left hand side, and we are left with the right hand. On the right hand side we have y prime times partial derivative of f with respect to y minus full derivative with respect to x of df dy prime. So notice what we got on the right hand side. In these curly braces we got Euler-Lagrange equation, and by definition this is 0, and so our alternative form of the equation therefore becomes d dx of f minus y prime df dy prime minus partial derivative of f with respect to x. So this is the alternative form of the Euler-Lagrange equation. Now you may say, how is this superior to the original form, given that now we have what seems like 3 terms as opposed to 2 terms? Well, let's consider the case when f has no explicit dependence on x. Then we end up with this full derivative being equal to 0, which we integrate and obtain the following: f minus y prime partial derivative of f with respect to y prime is now constant. So this in fact is very useful, as we'll see when solving various problems.